Swayam Prabha. Digital India. Educated India.
Hello everyone. So, in last session we have discussed the noise protection behavior of different types of nonwoven structure, including the struto structure, vertically oriented nonwovens. Now, we will start the composite structures. So, multiple layers are used with different types of combinations, like oven with non-oven structures are used for noise protection. The composite textile materials are also used in noise control, that is application where acoustic performance must be combined with functional and aesthetic requirement. So, that is important, that is a non-oven basically provides the functional aspect and the aesthetic aspect is provided by oven or knitted structure. So, that is why the composite structures characteristics one must know, study. So, rather than relying on single fabric type, composite structures often integrate two or more fabric layers like oven, knitted, non-oven. So, they ply one over other. So, to achieve multifunctional performance like acoustic with aesthetic, acoustic with the strength characteristic or abrasion resistance. So, for this we need the composite structure. So, in acoustic system, composites are typically consist of one layer is non-oven basically. So, one absorptive core will be there, which is basically non-oven, which is responsible for sound dissipation or sound absorption. So, in composite structure non-oven is used for basically sound absorption. Along with that, one or more layers of oven or knitted fabrics are used, which actually function is for protection and appearance, aesthetics. There is a study that studied the influence of fabric layout, different fabric layers and air gap between the layers on acoustic properties at low to medium frequency, where they have studied within the low to medium frequency. Now, these are the different layers of the oven fabrics, 1 by 1 plain weave, 3-1 twill, then warp reeve, then satin, different types of fabric structures, oven structures were used. Now, these are coded as like TP. TP is textured plain weave. So, the yarns used here are of two type, one is staple yarn, another is the filament textured filament yarn. Textured filament yarn is termed as T, coded as T, and plain weave is coded as P, S is satin is as like plain weave, satin is S and twill as T, okay, twill T, and this yarn rib as R. These are the fabric structure coding, and the yarn is that T is the textured, which is used at the first letter of 2 letter sample naming, and S is the staple. So, textured and staple. So, the naming convention will be for TP means textured yarn is used, textured filament with a plain weave structure TP. Similarly, SS staple yarn satin. So, these are the different naming convention. So, what has been observed that textured plain woven fabric has got maximum porosity, okay, among the woven fabric, whereas N stands for non-woven, which is having 97% porosity. So, maximum porosity is for non-woven. So, due to the high porosity of non-woven, these are used for the acoustic application, sound insulation application. Among the different weaves, plain weave with textured yarn had highest porosity. Now, we can see the placement of non-woven. The non-woven fabric is placed, is sandwiched in between the woven fabric, and the blue color it is a air gap inside the impedance tube. So, when it is tested, there is a air gap is created at the back side, and from this side the sound, that incident sound is there, and placing of non-woven and there will be a TP. TP means textured plain weave, TS means textured satin weave. So, textured and TP 3 layers of plain textured weave, then non-woven layer is kept, then followed by behind the non-woven layer there will be 3 layers of textured satin weave, and then air gap, and B configuration is that first satin 3 layers, then followed by non-woven and then textured plain. So, these combinations were used. Now, we can see that similarly there are many other combinations were made. Now, you can see here, this is the air through air, there is no that sound absorption coefficient of air is only air, it is a very low, and if we see the only non-woven, if we see only non-woven, this is better than only air, but there is a lower sound absorption as compared to the composite structure. Now, when with this non-woven structure, when we add this woven structure along with that, then the sound absorption coefficient increases, and here we can see that this one TS, texture satin, 3 layers, then non-woven, then 2 layers of textured plain. So, which gives very high that sound absorption at higher relatively around say 1200 frequency, very high sound absorption coefficient, but at different that sound level the trends are different, that we will discuss. So, here it is from this diagram it is very clear that the positioning of the different layers, they have significant impact on the sound absorption coefficient. In a composite structure. So, this result indicates a layering arrangement had strong influence on the acoustic performance. Best performance occurs when the non-woven is sandwiched between the woven fabrics compared to the woven fabrics in front and in the back. So, you can see here this one, these are non-woven fabrics in the back, and here non-woven fabrics, only non-woven fabrics in the back, if you see this is giving lower sound absorption coefficient, although the combinations are same. So, non-wovens should be sandwiched within the plain structure. Now, the same diagram. So, better absorption occurs here because sound wave faces multiple pore transition. So, woven fabric has got different pores, the next layer of woven fabric. So, they will come to that interaction with the next level of pore. So, in that different multiple pore transition will be there, which creates higher impedance mismatch. So, due to the multiple pore, the sound, when sound waves pass through the multiple pores, the higher impedance mismatch will be there. That will result the higher sound absorption coefficient. This transition increases the airflow resistance and friction loss. So, which improves the sound absorption. Sample with woven at front, okay. This is woven at front and non-woven at back, shows lower sound absorption like this two, woven at front and non-woven at back. These are the, it shows the lower absorption due to fewer structural transition. Now, which is very important, because the woven fabrics, they have the particular structure, definite structure, that pores have definite structure, and when they are passing through all the layers of woven fabrics, like 5 layers of woven fabrics, that is structural transition is not that high. So, that is why this sound absorption coefficient is relatively lower, but in case of non-woven comes into in between the woven fabric, that means the woven has got particular pores, followed by non-woven has their entirely different types of pore structure, and after coming out from non-woven, then when it enters to woven, again there will be different types of pore structure. So, this different types of structural transition will be there, different various structural transition, but which is absent when we are placing non-oven at one side. So, influence of placing the oven fabrics, position of plain wave. Now, you can see here, this is a non-oven air. Now, plain weave fabric when we are putting at front here, and in this plain weave we are placing at the back. Now, when we are placing the plain weave fabric at the back, we are getting very high sound absorption. In the front, plain fabric at the front shows excellent absorption at low frequency. So, here if we see this curve, plain at the front, which is showing the very good absorption at low frequency due to the open pore letting the low wave enters easily. The open pore here, the low wave is entering. However, this performance drops at mid to high. In this zone, the plain fabric at front is there is a drop. And when we place at back, that is shown by the red curve. This is the curve. What happens? Plain at the back showed strong consistent performance across from this range, from 400 to 5000 hertz. So, plain when we are placing at back, this combination gives very high that sound absorption consistently. So, this configuration is the highest NRC was better than the front in the plain layout. The plain weave has high interlacement and open pores, allows the low frequency wave to penetrate deeply and dissipate. That is why the low frequency in the wave it allows it penetrates. So, when you place the plain weave behind the non-oven, this is non-oven, behind the non-oven, the waves already are weakened by prior layers like satin and non-oven and air gap. Effectively, the remaining weak sound wave can be trapped in the plain fabrics. So, here when the weak wave will be trapped better way by the plain fabric. So, strong wave, sound wave will not be trapped if we place when we place the plain weave at the front. So, satin weave basically has a lower interlacement, smooth structure, smooth surface, yarn floats are more. So, which results in the different pore geometry. So, it is the pore geometry will be entirely different from the plain weave. The opens pathways, but is effective than plain weave to at manipulating at low to high frequency level. So, another study also dedicated to sound absorption characteristics of multilayer nanoven. So, here the multilayer nanovens were produced. So, this is the single layer nanoven by shown by the sky blue, which is coded as K, with this is made from the kapok, and polyethylene film, which is a light green color, which is represented by P. So, that multilayer formation was done. So, this is one layer nanoven and kapok, and when two layer we are using nanoven is at the top, kapok K and polyethylene at the bottom. So, it is coded as Kp, and when we reverse the two layer Pk, similarly one nanoven layer K kapok and two polyethylene layer Pp, Kpp, Pkp, Ppk. Ppk means two polyethylene layer at the top and nanoven kapok nanoven K at the bottom. Similarly, the 4 layer was formed KKPP, KPKP, PKKP, that means both the sides there will be polyethylene and 2 layers of kapok will be there. So, similarly, the PKPK and PPKK. So, here in 4 layer we have seen that 2 layers of nanovens are used and 2 layers of kapok, and 3 layer in 3 layer configuration where we have seen the single layer of nanoven and 2 layers of polyethylenes are used. So, in this way the different layers 1 layer, 2 layer, 3 layer, 4 layer configurations were studied with a different coding system. So, needle punch nanoven K, which is made of 90% kapok and 10% hollow polyester, and polyethylene film of varying thickness was studied. The PE film and needle punch nanoven fabrics were thermally molded in a oven to get a single composite structure and then air cooled. So, we got the composite structure here, and this structure was actually this composite structure was tested for the sound insulation characteristics. Now, here we can see the sound absorption coefficient like Pk, Pk, Kp and Pk, that is polyester, that is K is that the polyethylene P that has got lowest sound absorption coefficient, then K is the kapok, which is red color, but when we use the combination kapok and at the bottom we only keep the polyester polypropylene. So, kapok and that nanoven and polypropylene, then we found that there is an increase in sound absorption coefficient. But in case of polyethylene, if we put at the front and then this is polyethylene and the nanoven when it is put at the back, nanoven, that is K, kapok nanoven, then we found that there is a significant increase in the sound absorption coefficient up to say 700, 800 hertz frequency, but after that when it crosses, then there will be a significant drop in the sound absorption coefficient at higher frequency. That may be due to the presence of polyethylene foam, polyethylene sheet at the face. Here you can see that the sound absorption coefficient, this is for the 3 layer structure KPK, PK and PPK. So, you will see that when we use the polyethylene at the front, okay, maybe a single layer or double layer. So, there is a after certain sound absorption initially, then there will be sudden drop in the at the higher frequency level. So, at lower frequency level, when we put the polyethylene at the face, then sound absorption will be very high, but at higher frequency level there will be significant drop. Now, these are the 4 layer. In 4 layer the similar trend is observed. Now, let us try to see the resultant that wave, that these results indicate that the layering sequence has strong influence on the effective, the resultant sound absorption coefficient. So, that single layer has got certain sound absorption. If we have multiple layer, there will be some resultant sound absorption. So, if we have different combination, different layering pattern, that will have significant impact on sound absorption. Now, surface impedance analysis shows that sample Kp, KKP, KPP and KKPP, they actually real impedance value close to 1, that is non-oven at the front, imaginary impedance value close to 0. So, this is the Kp. So, here impedance value, real impedance value, that is this is a real impedance value close to 1 and imaginary impedance value close to 0. This is surface impedance analysis, which indicates the lower reflectance, lower reflection of incoming sound at the surface, greater transmission of sound energy into the material, higher internal energy loss within the porous layers, and this combined effect results superior sound absorption performance. So, where we use this type of layering, the porous material backed with a flexible membrane like polyethylene absorbs sound better than those placed against the rigid backing. So, porous material like non-oven, if we use the backing with the flexible membrane, that will result higher sound absorption. The membrane vibrates under the sound and which cause the actually the absorb the sound energy. So, this and whereas the rigid material will not vibrate that much. So, additional scattering of incident sound will take place, enhance the dissipation of acoustic energy. So, overall membrane porous composite shows the improved acoustic behavior due to both reduced reflection and increased internal loss. Increased internal loss is the basically due to the porous material reduced reflection due to the dissipation of the acoustic energy, light that is sound scattering will be there. The real and imaginary part of the specific surface impedance of 4 layer material are similar to those of the 2 and 3 layers of material. So, that is the observation. So, position of PE film significantly affect the acoustic characteristics of multi-layer composite. So, we can see here the sample PK one. So, PK where this polyethylene, flexible polyethylene layer is placed at the front, the sound absorption coefficient is higher than the Kp, that is the when the nonwoven is kept at front at a frequency below this, at this frequency level. So, here where Pk is higher than Kp, but it becomes lower above this 1117. So, above this from this level, so above 1117 hertz. So, this becomes much lower. At low frequency, why this is high at when the that polyethylene is kept at the front at low frequency, polyethylene film and porous layer acts together as a resonant cavity system. This configuration generates a strong absorption peak around 780 hertz. If you see that 780 hertz here, strong absorption peak is generated. However, this resonance effect also leads to reduction in absorption of mid and high frequency also. So, even for 3 layer material, peak absorption sample PPK shifts towards the lower frequency as compared to PKP. A similar trend is observed for the 4 layer also. So, moving the PE film changes the resonance behavior, thus adjusting the position of PE film shows there is a sudden change in the absorption behavior of the material, sound absorption behavior. There is another study, there is a hybrid nonwoven structure and compared their acoustic property of melt blown and needle punch nonwoven. So, that melt blown and needle punch nonwoven, they have the composite they have produced, and the fabrics are made up from the polypropylene fiber. So, hybrid nonwoven fabrics developed besides the needle punched and melt blown fabric. So, they have produced needle punched fabric, they produced separately melt blown fabric, and then melt blown and needle punched hybrid fabrics also produced, and comparative studies were carried out. So, these are the thicknesses. GSM 210 fabric sample and fiber diameter was used 19. This is the micron meter, 19 micron, not millimeter, it is a micron. So, molten polymer was sprayed directly onto the needle punched fabric. This formed a melt blown layer either on the top or on the bottom. So, bottom. So, there is a needle punched fabric, this is a needle punched fabric, needle punch, and the melt blown fibers are laid on the nonwoven fabric, form a layer. This layer may be at the top or at the bottom of the nonwoven fabric, needle punched fabric. Now, the coding is that MB 23 means the screw speed is 23 rpm, MB 28 means screw speed is 28, where and the sample size is given. So, sample size is 0.5 square meter and thickness is 2 millimeter here, okay, and weight 207 gram per square meter, and for MB 28 212. So, these are the parameters for the melt blown, and here it is a for the needle punched, and they are sandwiched. So, this is actually 210. Okay. So, this is the characteristics of the parameters for the this composite structure, needle punched and melt blown. So, this is the total parameters. Here is the only fabric parameters are there. So, initially the thickness was 2.4. Now, after this there will be different thicknesses are there. So, calendaring was carried out using two heated roller, spun bonded the fabric and the spun needle punched and melt blown fabrics were there, and the sound absorption characteristics were measured for the needle punched, melt blown and their combination. Now, here there are combinations are there. This is only needle punch. So, S1 is only needle punched, S2 is melt blown, 23 the screw speed rpm, and S3 is melt blown, which is NP it is called. S3 is the melt blown, only melt blown with 28 screw speed, S4 melt blown 23 plus needle punch, first melt blown, then needle punched, S5 needle punched and melt blown 23, S6 melt blown 28 and needle punched, and S7 needle punch and melt blown. So, S4 and 5 the difference is basically the which is coming in the front and which is coming in the back. Similarly, for S6, S7. Here we can see clearly the location, that is position of the this fiber and layering, the making composite, they have significant impact on the sound absorption coefficient. Now, we can see here the black is the normal, this is not the, this is without any that is standard base. Now, S1 is having very low sound absorption, that is only non-woven. Okay. But the S5 has got very high that sound absorption factor. What is S5? We can see here, this is S5, needle punched with melt blown, and S7 is needle punched with melt blown 28. So, S5 and S7 they produce. So, S needle punched when it is coming in the front one side and then followed by the. So, here you can see that melt blown is coming at the top and needle punch S5 is melt blown is coming at the top and then needle punch is at the back. Similarly, for S7 melt blown is coming at the front and face and the needle punch below that. So, these two configurations results very high sound absorption. So, needle punch non-woven S1 alone show lowest sound absorption across the all frequencies. Melt blown fabric both the RPM S2 and S3 perform significantly better than the needle punched material. So, S2 and S3 they perform better than the needle punched fabric. Melt blown sample produced in 23 RPM S2 showed higher absorption than 28 RPM. So, 23 RPM it shows little bit higher absorption, particularly at higher frequency level. So, fiber diameter in 23 RPM screw speed melt blown it is 1.18 micron. So, fabric contributes to the superior acoustic performance. So, at 23 RPM, so it gives a very good acoustic performance. The hybrid structure with melt blown on the face and needle punch at the back showed higher sound absorption. So, melt blown at the face and the needle punch at the back it showed very high sound absorption. So, melt blown has got very fine fiber diameter, typically around 1 micron, 1.5 micron, and that results different pore structure and also very high fiber surface area, that results very high friction loss. So, at the face if we provide the melt blown and then followed by at the bottom at the back side if needle punch is there, that type of combination produce very high sound absorption coefficient. This improvement occurs due to finer fiber diameter and larger surface area of the melt blown layer, and which results in higher frictional loss. Thus, it can be said that placing the finer fiber layer on the surface improves the acoustic performance of hybrid layer. So, hybrid fabric. So, we can make the layered structure for better acoustic performance, not made of a single type of single fiber, but for multiple layer with a different types of pore structure. Additionally, needle punched and melt blown hybrids slightly outperform melt blown only. in the sound absorption, only melt blown. So, if we think that okay, can we use only melt blown? So, only melt blown will not have that much better performance. Now, the different applications of non-wovens in acoustic application. So, these are office, studio, classroom. So, these are the different applications like in panels, ceiling, tiles, wall lining, in machinery and duct lining also we can use, like in generators, compressor, HVAC unit. So, in washing machine, so to reduce the sound level, in automotive sound insulation we can use, and underlying floor carpets. So, there are different applications where we can use non-woven fabrics. You can see these are the different applications. The picture shows in the building construction. So, insulation we use the non-woven backing for sound insulation. So, in the flooring, below the floor we can use the non-woven for sound insulation. In the below the seat cover, this is for the basically for sound absorption, otherwise there will be echoing in the hall. So, these are different typical applications. You can see these are the duct liner. In the duct there will be huge noise will generate. To actually reduce the noise level, there will be liners for the acoustic liners are there. So, different types of duct liners are used. In automotive we can see different applications where non-wovens are used widely for sound absorption. These are the typical applications area. Now, the overall summary of the protection against noise, role of textiles in noise control. So, noise control is important for human comfort and health and safety. Textiles are widely used in acoustic application due to their lightweight, flexible and porous nature. Among textile structure, non-woven fabric is the most commonly used and most widely used material for sound absorption. The fiber arrangement, the bulk structure govern the acoustic performance of non-woven, not just the raw material. Key influencing factors including fiber type, fabric thickness, density, porosity and processing parameters are important for sound absorption. Controlling the structure and processing parameters, which will actually affect the sound absorption and noise reduction. Textile based acoustic materials are extensively used in automotive, building, industrial application and environmental applications. So, these are the overall summary of our different studies. So, based on this idea, one can think of having a very good noise protection. Now, in this session we will continue with this session with our research in-house, which we have done, we have carried out. We have carried out different types of research on different knitted fabric we have studied on non-woven fabrics, and also we tried to simulate the this actual running condition of the automotive insulation where vibration is there. So, we have developed one instrument, this we will study, we will discuss here. So, acoustics of nonwovens. So, that is thicker nonwovens, that thicker nonwoven with higher noise reduction, especially at low frequency. This is the study we have carried out. So, we have changed the thickness of nonwoven. So, 3 millimeter, 6 millimeter, 9, 15, 20, 4 millimeter. What we have done? We have produced a nonwoven with the 3 millimeter nonwoven. Okay. Then we have used a 2 layer, it becomes 6 millimeter, 3 layer, 5 layer. Okay. In that way we can have different layers. So, what we have observed, as we increase the layer, okay, so it has become 24 millimeter thickness, the sound absorption coefficient increases as the thickness increases. Similarly, noise reduction coefficient also increases with the increase in the thickness of nonwoven. So, effect of layering, we have done 2 multi-layer configurations were designed to study the layering effect on sound absorption. So, what are these? Set S. Set S consists of the overall thickness, where we have kept the constant overall thickness. So, we have changed the number of layer, but overall thickness was kept constant. Total nonwoven thickness was kept constant for all samples. Layer configurations are, you can see the layer 1. So, one layer is basically S1 is the one layer fabric, we have kept the certain thickness. Okay. Then we have done the 2 layer S2, same thickness was kept, but there is a there are 2 layers. Okay. This way, so 3 layer configuration, 3 layers were there, but with made up this S3 is a 4 layers, this is 4 layers made of the same thickness were made, but with the 4 layers, and 6 layers same thickness with the 6 layers. Similarly, with the 8 layers. So, layer number of layers were changed, but thickness were kept constant. Similarly, in set A, this is called set S, okay, and in set S, set A constant aerial density was kept constant. So, total aerial density were kept constant. So, layerings were again A1 is with one layer, A2 is the 2 layer, A3 is the 4 layer, A4 is the 6 layer, and A5 is 8 layer. So, these are the S series and A series. S series for keeping the thickness constant, A series keeping the aerial density constant. So, both multi-layer sets were shown very small variation in the NRC. So, there is no such variation in NRC is there, noise reduction coefficient. You can see the set S means the thickness was kept constant. In thickness, when thickness is kept constant, the noise reduction coefficient. Noise reduction coefficient is changing within the 0.54 to 0.6 with a very low range. Even for sound absorption coefficient, there is no significant change, difference is there. And set A, when we are changing the this keeping the areal density constant, where when we are changing the this number of layer, again there is not much change, 0.54 to 0.66 this change, okay. Even though not so significant difference is there, but still this A1 with a single layer, A1 with a single layer or S1 with single layer shows the least sound absorption coefficient or noise reduction coefficient within that range, but there is a trend. If we increase the at least for the for keeping the same GSM areal density, when we increase the number of layer, the noise reduction coefficient increases consistently. So, layering improves the sound absorption as the multi-layer specimen performs better than the single layer nonwoven. So, here you can see the this is single layer. So, when we make the multi-layer, there will be improvement in, and this is the 0.54 to 0.6, although it is not too high, but there is a improvement is there. So, effect of stacking on sound absorption. So, if we in place of one layer, if we use two layer, what will happen? In between the layer there will be a gap, air cavity will be created. So, when we use the in place of single, there is a single layer, in single layer there keeping the same thickness, two layer and single layer, or maybe keeping the same GSM areal density, one layer, two layer there is a cavity, air cavity is created, which it goes through multiple reflection will be there within this cavity. So, that is shown here, multiple reflection in the cavity, and each instance of reflection results a decrease in the sound energy. So, that due to this multiple reflection, the sound energy will decrease. The rough surface of the wall cause the sound scattering inside this. Here rough surface is there in the nonwoven, there will be a multiple scattering also will be there, and that will actually hence a disturbance in the sound propagation occurs. So, multiple reflection and scattering will be there, that will result higher sound absorption. So, the repeated variation in material density results viscous loss also, because there will be relatively denser surface material for nonwoven, and when it comes to the air cavity, the material density variation is there, and which will result a viscous loss will be there. So, this is the study which we have carried out to use the multiple layer effect of multiple layer, keeping the thickness or areal density same. And next study we have done different studies. So, next study was the effect of compression on layered nonwoven assemblies. So, that we will discuss in the next session. Till then, thank you.